Cool. So before getting started, I want to say that this is joint work with Brandt, Sylvan, Matt J, Matt P, Guido, Eric, and Tobias. It is not just me who is presenting this. So the work I'm presenting is a design paper. It introduces a dynamic ownership model which can be retrofitted into dynamic languages. Yes. The work itself is language agnostic, but we have designed it specifically in the context of Python, and with the goal to add true parallelism to Python. Currently, there is one limitation in Python that makes this difficult, and that is the global interpreter lock, also called the GIL. While it prevents breakage by making sure that Python objects are only modified when this lock is held, it also sequentializes programs and makes them slow. This makes sure that the reference count is correct, but it is a really big bottleneck. This is why there's a community effort going on to improve this. One of the big ones is PEP 703. This one proposes to make the global interpreter lock optional. This effort is also commonly called free-threaded Python or no-GIL. You might have heard about it. The second big proposal in the community is PEP 734, which proposes adding subinterpreters which are completely isolated. To share information between two subinterpreters, you actually have to serialize the data and send it to a different subinterpreter. Now that I've given you the context, I will give you an intuition how Python works in these regards and where Langfish comes in. So first, let's take a very simple Python program, a single-threaded one. We can represent the memory as the green area over here, and we have a single thread, which is a thread emoji, which has access to objects. Slight bit to make sure everyone understands. The arrows are references, and the objects are the blue circles. Now, if this thread would want to do some modification, for instance, increment our number by 1, it is super easy. It can just increase it. Not a problem. We don't have any data races. Now, in free-threaded Python, which wants to propose to remove the GIL, we can have multiple threads living in the same memory space. And these, living in the same memory space, are allowed to create references to all objects. And thus, we can have a situation like this. Now, incrementing integers can be hard. So let's try to split the work across two threads. And when we do this, and they are both super fast, then we have a data race. And this data race comes down to a central problem of having shared mutable state, in this case, this object. Now that I've given you an introduction of free-threaded Python, let's revert the time a little bit to our number 42 and use subinterpreters. I mentioned that subinterpreters are completely isolated, so they don't have shared memory. And to here split work, you actually create a copy, send it to a different subinterpreter, and now both of them can do the amazing work of adding 1 to our numbers. But we still don't have the result we want. We wanted a 42, and now we have two objects, two versions of the same object from what we expected with the value 43. And this is where our ownership model comes in. Our ownership model ensures exclusive access to mutable data at runtime. And it is called Langfish. And it is called Langfish because it can work with the GIL, with the global interpreter lock, and without GILs. So before giving you an intuition of how it directly works, with the no-GIL effort, it allows you to reason about data races and prevent them all together, while with subinterpreters, it allows sharing across subinterpreters without breaking isolation. So let's start this by adding a region. Langfish manages ownership on a region level, so on an isolated group of mutable objects. You notice that the region, which is the yellow blob in the middle, is not dedicated to one single interpreter or memory region, but it's in the middle. And we have the green object up there, which is called the bridge object. This is inside the region and acts as a handle. Now, we are in a dynamic world, which gives us some flexibility. So to transfer ownership, we actually just have to do a field assignment, and as a side effect of this assignment, as a side effect of creating a reference from our bridge object to the blue object, the ownership is transferred into the region. Another change you might have noticed is that the arrows going from the thread into to the objects are dotted. And this is because these are not owning references, these are borrows. This is very similar to the Rust model, where it is a reference where you can read, and in this case also always manipulate from, so mutate, but it is not the owning one. The owning ones are solid. Now, let's go through our example again where we want to increment our number. So our thread 1 has right now mutable access, so it could increase the number. However, with Langfish, we can prevent any other thread from having mutable access at the same time. So reference from thread 4 would not be allowed. To actually transfer ownership, to actually allow thread 4 to access it, we have to first remove our references from thread 1, and then we can create new references. Once we have a reference to the bridge object, we can access contained objects and do our magical addition. Now, Langfish is a memory model, and it is concurrency model agnostic. Here I will show you a model how it can be combined with locks to make parallelism and concurrency safe, but there are other concurrency models you could combine them with. So let's introduce our lock here. And since it's a lock, which can be a primitive, a safe primitive, we can have two threads accessing it. But critically, right now, the lock is released, so none of them have access to the contained data. To actually do the mutation, they first need to acquire the lock, indicated by the key, and then they can create borrows into the region. Now we can do our addition super easily. In other languages, there's a common problem of what happens when you now release the lock. How with Langfish, we can prevent this. We can specifically detect these things and throw an exception, and saying, if you release the lock right now, there could be a data race because you still have residual references. To actually release the lock, we have to remove all borrows, burn them, and then we release the lock. After we've released the lock, thread 4 can acquire it, also do the addition, and we again get the expected result of 44. Once the reference is removed, we can again release the lock. So now that I've given you an intuition, I wanted to talk about some goals we had with Langfish. First, we wanted to have no concurrent mutation to prevent data races. We wanted to facilitate ownership transfer, and have control over sharing. Another advantage is that we can bound access. So for instance, if you give a region to an external library, you know that it can only access objects in this region. But Langfish wasn't designed in a vacuum. In fact, it was designed in the project for Python. So this comes with certain challenges. One of them is the non-existence of static checking. Typically, ownership models have been predominantly implemented using static type checking, but we don't have that in Python. Python is dynamic, and it can do a lot of things during runtime. It's actually amazing. The next problem is that we don't have type metadata. A lot of other ownership models use type annotation and so on to say where and how ownership might flow, but we don't have that in Python. And the last one, which I think is also super critical, is that there's an existing ecosystem. In theory, you can design the best ownership model in the world, but if it would break the entire ecosystem of Python, it would not be used. It would not be applicable to this case. Now that I've given you an introduction and an intuition, hopefully, of what Langfish does, I also want to give you some limitations which we needed to add to Langfish to make this efficient to implement. For this, we have a thread in our region here, and we can add a sub-region. So this is simply a second region, R2, and we are allowed to reference the bridge object with a single reference. As long as this one is unique, everything is fine. But if we would now try to create a reference from C to R, that would break uniqueness. But the good thing about this is we can throw, again, a nice exception explaining that this region is already owned, already referenced, and this reference is not allowed. I want to say this is just about owning references. Borrows to the bridge objects are totally allowed. Another restriction we have is that isolation cannot be broken. So I've mentioned that regions are isolated group of mutable objects, and all references to these objects have to either be borrows or come from inside the region. It is not allowed to create a reference from our C object here to our D object. Now, after the restrictions, I want to talk a little bit about how Langfish can be implemented. So to implement it, we envision using a write barrier. And this write barrier does a few things. One of the things is that it assigns ownership on objects. This is one of the first things I've shown you where the assignment of a field actually transferred the ownership into the region. Then it tracks external uniqueness, and to implement this efficiently, it maintains the local reference count. The local reference count can be seen as the number of borrows going into a region. So you can see right at this moment, our region 1 has a local reference count of 2 because we have 2 borrows coming in, while our region 1 has 2 references coming in, while our region 2 has no borrows and would be safe to send. Now, if we would add a reference going from the thread into our region 2, the write barrier would increase the local reference count, and to prevent the parent region from being sent off, it would also propagate this change upwards. Now that we've incremented the local reference count, the write barrier is also magically able to decrement the count when references are removed, and this that has the same spiel of decrementing the parent local reference count. So, I've mentioned the write barrier. What implication would this have for the actual implementation of the interpreter? Any field assignments like this one, x.f equals y, would have to be slightly rewritten to store the previous value in a temporary value. Then we would call the write barrier, and if the write barrier succeeds, so throws no exception, then the assignment can be done. This write barrier, or this might look like a little bit of a rewrite, but I want to remind you that Python already has a write barrier for reference counting, incrementing, and decrementing. Our paper actually includes a mock pseudocode for the write barrier. This looks like a lot, but the fast path is actually highlighted in green and comes down to 2 if statements, which should always be true, unless you use ownership in some edges, and the reference count increase and decrease. I've mentioned that this is the design paper, and as part of the paper, we've also implemented FrankenScript, which is a dynamic language with Python-like syntax and semantics. And this one actually generates automatically the diagrams I've been showing you to give you an intuition how it works. This has been invaluable to communicate inside the DEAM and design things. So thus far, I've talked about the design in PLDI. Next steps for us is the implementation. This is a picture of us visiting the US in May to present our work at PyCon US. We have also been in constant feedback with C Python developers. A special shout out to Brandt, Guido, and Eric, who have given us invaluable feedback and helped us a lot with our work. The paper, as a design paper, contains a lot. Especially I want to highlight some of the cases you could have because Python is still a dynamic language, and that is handling reflection in mutable types. In Python, everything is an object, even a type, with lots of beautiful cycles. We also have the ownership rules specifically defined, and I encourage you to read it. In summary, we have designed a dynamic ownership model called Langfish. Langfish enforces exclusive mutable access at runtime, tracks ownership for a group of objects, and throws errors before data races can happen. It allows cycles, which is important to support existing topologies, and can be retrofitted into dynamic and gradually typed languages. I've explained this all in the context of Python, but we have also spent a little bit of time considering how it might be applied to other languages. It also can allow true parallelism without substantially rewriting the Python ecosystem. At least that's the work we are doing and aiming for. Thank you very much for the attention, and I'm happy to take any questions.
Please state your name and your affiliation.
Nick Swami, Microsoft. Great talk. There's one thing I didn't understand. In your initial example, you have one of the threads has a reference to a sub-object in one of the regions, and then when it's done with it, it burns it. And now, if I want to regain a reference to that object, do I have to traverse the entire object graph from the bridge object to find it again?
Yes. Right. You would have to do that right now. Potentially, so one of the things is that this is concurrency model agnostic, right? So we enforce complete isolation of the region. There might be some design space to have not weak references, but references that only are active in these cases, but we haven't explored that space a lot yet.
Thanks.
Good question.
Thanks.
Hi, thanks for the great talk. Leonard from University of Montreal. I was wondering, if I understand correctly, you have to create those regions manually. Mm-hmm. So how big do you think those regions will be once implemented in Python, or what kind of regions do you think you will have?
So this is a complicated question and touches a little bit on something which was not in the talk but is more in the paper, and that is immutability. So if you would always move all types and everything into these regions, they could become quite large. But you can make certain parts immutable, which allows references from multiple regions. And thus you could shrink your regions or share data across regions and only really share the mutable data. So there's room for optimization if you want to. We don't really have an estimate for how big these can be, but we've tried dumping some object graphs of Python objects, and it's surprising how big they can be. At the end of the day, it's also, once you engage with Langfish, you will add parallelism, so the speed up is probably, or should be way above what you get just from these changes.
Okay, can we have the next speaker please come to the front? Sorry, just set up your laptop, yeah.
Yeah.
Do we have more questions? Okay, so let's thank our speaker again.